Hello everyone. In this video we will define the prime numbers and present some facts about prime numbers. And the way you might have defined prime numbers before, I'm going to give a slightly different definition of prime numbers, but then I'm going to connect that to the definition that you might be aware of. The number one in the set of integers is called a multiplicative identity, and the reason for that is that it satisfies this property that k times 1 is k for any integer k. Now, an integer m is called the multiplicative inverse of another integer n if m times n is equal to 1. And so if m times n is 1, then we use the notation that n to the exponent -1 is equal to m. So let's observe that we are talking about two integers m and n. Now what's the inverse of 1? Well, the inverse of 1 is itself, because 1 times 1 is equal to 1, so 1 is the inverse of itself. What's the inverse of -1? Well, -1 times -1 would be 1, so the inverse of -1 is itself as well. And in the set of integers, these are the only two numbers that have multiplicative inverses. So these are another way of saying that is that these are the only two numbers that are invertible within the set of integers, and there are no other integers that are invertible in Z. Now, of course, the numbers like 2, 3, 4, they are invertible in the set of rational numbers or in the set of real numbers, but they are not invertible in the set of integers. So they don't have inverse. So 2, 3, 4, they don't have inverses within Z. So here are two definitions. The first definition is that of an irreducible integer. So a non-zero non-unit. Okay, so what do we mean by a unit? So when I say a unit, I mean it's an invertible element. So if I say it's a unit of Z, it means it's a invertible element of Z, and there are only two units in Z, as we said, 1 and -1. These are the only two units, meaning these are the only two invertible elements. So a non-zero non-unit, which simply means a non-unit simply means not plus or minus 1. So a non-zero non-unit integer n is said to be an irreducible integer if its only divisors are plus or minus 1 and plus or minus n. So if I ignore the negatives, then we are saying that an integer is an irreducible integer if its only divisors are 1 and itself. And if you recall, that might be the definition of prime numbers that you have used before. A non-zero non-unit integer n is said to be composite if it is not irreducible. Okay, so what's the definition of a prime number that we are going to take? A non-zero non-unit integer p is said to be a prime number if it satisfies the following property. For all integers a, b, if p divides a times b, then either p divides a or p divides b. So the reason I'm defining the prime numbers in this way is because that should be the actual definition of prime numbers, and there are within the set, we're going to see in a bit that within the set of integers, these two definitions are equivalent. But there are other sets of numbers where these two definitions are not going to be equivalent. So here's the theorem that says that those two definitions are equivalent. So a non-zero, non-unit integer n is a prime number if and only if it is an irreducible integer. So essentially, this theorem tells us that the two definitions in the last slide are equivalent. All right, so in the next video, I will go over proof of this theorem.